see. Hello, I guess it's time to start. So, first, is there any question from this time? Hello, please be quiet. Yeah, and this time we talk about some. I guess that's still a few review back. Okay, so we talk about some transformation and the properties you can have on signals. So we see that there are three changes of the independent variable that you can do on your signal. There are time shift, time reversal, and time scaling. Time shift, you shift your signal to level right, and time reversal, you put a minus sign on your time, and so your signal flip left and right. And time scaling, you scale your time by some constant, and it's easier to define for continuous time. And for continuous time signal, you either stretch or shrink either stretch out your signal or shrink your signal. Okay? And then there are some symmetry properties related to those changes in the independent variable. So the first property, which is most important, very important property, is a property that I will study basically throughout the whole course, is periodicity. Okay, so there are periodic signal, means that it's a signal that repeats itself, keep repeating itself through go to positive infinity and negative infinity. Okay, and mathematically it's written in this term. So x of t equal to x of t plus some big T, and big T will be a period. Okay, so this means that you shift the whole signal to the left by big T, then the signal doesn't change, and that can only happen if the signal keep repeating itself. And we define T as some positive number. And similarly, we have this definition for discrete time signal. Okay, so this is periodicity. And then we say, so another very important concept here is fundamental period. So a signal can have many periods, because for any period you have, twice, 3 times, 4 times of the period as a still period of the signal. But there is almost all the time there is a smallest one of the period, and that will be called fundamental period. And there is one exception, which is the constant signal, which has no fundamental period, because any number will be a period for the constant signal. You can shift it by arbitrary continuous amount. Okay, and so that's a periodic signal. And then we also define even and odd signal. Those are also nice symmetry with respect to this time reversal. Their definition on this. So even signal, if you reverse the time, you apply the time inversion, and the signal still the same. And for other signal, when you invert time, you get a minus sign. Okay, but most of today we'll be discussing periodic signal. Okay, and to discuss periodic signal, then now we come to those complex exponential and sinusoidal. Okay, and complex is so. It's complex exponential, and it's really related to complex analysis. And two of the most important rule we use in complex analysis is this, I guess, basic one relation. It's this Euler relation, which says e to the j theta equal to cosine theta plus j sine theta. And this allows us to express a complex number very complexly in the basically the polar coordinate. Okay, so we think about a complex number is some number with a real part and a imaginary part. So real part is sigma, the imaginary part is omega, and then we can also express it as its absolute value. So this r equal to absolute value of z, and times e to the j theta. So where this theta is this angle between this line to the real line. Okay. So so you can express your complex number as sigma plus j omega, the real part plus imaginary part, or r times e to j theta, where r is the radius and theta is the angle. Okay, and this can be derived from the Euler relation. And then we also sometimes use this reverse Euler relation that will break cosine theta and sine theta into linear combination of e to a j theta and e to a minus j theta. Okay, and anyway, so complex exponential is an exponential function with a whole bunch of complex coefficients. So it's in the general form, it's c times e to the at, where c and a can be both a complex number. Okay, and so for special case, if everything is real, then we have this exponential growth and exponential decay that you're probably familiar with for the complex for the exponential function. And but the one we care about are periodic complex exponential, because we want to study periodic function. So for periodic complex exponential, they are complex exponential of this form. So you can have basically arbitrary c that's not zero, then times e to the also zero, I guess is okay. But c times e to the j omega naught t. And so this means that a is purely imaginary. So if your exponential part is purely imaginary, then we see that this function can be basically can be periodic. Okay? And then we can solve for when it's periodic, excuse me, and then we can solve for its period. Its period will be 2 pi divided by this absolute value of omega 0 or omega naught. Okay, and from this you see e to the j omega naught and the e to the minus j omega naught has the same fundamental period. Okay, and so they are both rotating, and we now have a better visualization of this periodic complex exponential. So whether this thing is periodic, because you think about basically e to a j theta. So back to this picture. So from Euler relation, we have e to a j theta, where theta will be this omega naught will be omega 0 t. Our function is e to a j omega 0 t, right? So we should write it here. So our function basically is some constant times this e to a j omega 0 t. Oh, let me try to find my pen. Yeah. So our function is wait. Function is e to the j omega 0 t, e to the j omega 0 t, and then we think about what does this value look like on the complex plane. Then it's working on this circle, because it will be something with so it will be a complex number with this radius 1 and with the angle. So this theta will be omega 0 t. Okay, and or sigma will be omega t. Do we say omega 0? I guess we omit the 0. So g to a j omega t, okay, and omega t will be theta. So when t go from 0 to infinity, then you see, or I guess t from minus infinity to infinity, then you see that the number is just keep working on this circle. And in particular, when t equals 0, then you have theta equals 0, then your function is a value here, and and then when omega t become 2 pi, and that's when when omega 0 t become 2 pi, that's when you reach your fundamental period. Then you walk one circle back to this point, and then you see that you will complete the period. Okay, so so omega t from 0 to pi over 2 to pi to 3 pi over 2 and to 2 pi, and then you see you complete a circle. Then you keep increase omega t from 2 pi to 4 pi, then you see you just loop around a circle. And you can also see this periodicity from analyzing the real part and the imaginary part of e to the j omega t. And so the real part will be cosine omega t, as we know from Euler's relationship, and the imaginary part will be j sine omega t. And we know both omega t and the sine omega t has this fundamental period of 2 pi. Okay, and yeah, so this is why e to a j omega t is working on this circle and has a period of 2 pi divided by omega 0. Okay, everyone okay with this complex exponential? Okay, and yeah, so that's why complex exponential with a purely imaginary exponent is a periodic function. Okay, and this will be building block of every periodic function we'll see as we later do further analysis. Okay, and so that's complex exponential, and we also want to talk about sinusoidal. And for me, sinusoidals and complex exponential are basically the same thing. But anyway, sinusoidal functions are a function of this form. Well, now it's a real function. Yeah, usually it's a real function. But let's see. It's a little annoying. Well, so I guess a can be complex. But anyway, sinusoidal function is a function of this form, x of t equal to a cosine omega t plus phi. Okay, and yeah, and as we say, so omega naught and phi here omega naught and phi are real, and a can be a complex number. Okay, and so this is really similar to complex exponential. Anyway, so this is a periodic function. Because if you draw in a picture, it looks like this. Okay, so it has so assume a is real, then you can draw on just a plane, and so it's a well cosine function with height a, and it's shifted by some phi, and it has a period 2 pi divided by omega 0. Okay, and so its fundamental period, very similar to complex exponential, is 2 pi divided by omega 0, because when omega naught t go from 0 to 2 pi, this thing goes through one period. Okay, and okay, and there are some other notations. So there is a and so some usually this omega naught has units radian per second, and sometimes you also want to see how much cycle per second your signal is oscillating. Then you will change from omega naught to f naught, which f naught is 2 pi times omega naught, means f naught is omega naught divided by 2 pi, means f naught is how many cycle per second this signal is having. Okay, and anyway, so why do I say complex exponential and sinusoidal functions are really similar? Because you can always express complex exponential as a combination between sinusoidal signal, or you can express the sinusoidal signal as a complex exponentials. And so, for example, you can just use Euler's relationship to write a complex exponential as a summation of those two sinusoidal functions, and you can use our reverse Euler to write sinusoidal signal as a summation of those two complex exponential. Okay, and yeah, so you can check the math detail yourself, but in general, it's pretty straightforward to convert between complex exponential and sinusoidal signals. Okay, and also another way to get sinusoidals in terms of complex exponential is that you know the real part of your complex exponential is cosine sinusoidal, and the imaginary part is sine sinusoidal, etc. Okay, and but for most of the course, I guess I'll say a little more. And so why do people like sinusoidal? Because sometimes they can be purely real. So if we pick a as a real number, then this is a real function, and it's easier to plot and visualize. Okay, and indeed, usually when we plot our complex exponential, we just plot basically the real part, and we plot the sinusoidal to express our complex exponential, because complex exponential are complex functions, and it's usually harder to plot complex numbers. Sorry, a complex function, and but for the mathematical construction, we will usually work with complex exponential to express our Fourier transforms, etc. Okay, but it's nice to know the mathematical connection between sinusoidal function and the complex exponentials. Okay, and so that's sinusoidal, and okay, let's go back to our complex exponential, and there is this new concept of fundamental frequency. Okay, so for complex exponential, we see that this fundamental period is very related to this number omega 0, and so we call this number omega 0 as a fundamental frequency. And we know fundamental period is 2 pi divided by the fundamental frequency absolute value. Okay, So basically, this is just a definition. This omega 0 absolute value is I guess the fundamental frequency. We didn't say very. Oh, never mind. Yeah. So this absolute value of omega 0 is the fundamental frequency. Okay. And yeah. And then there is a special case. So for omega 0 equals 0, then as we mentioned, this is a constant function. So this is where fundamental period is not defined, but actually fundamental frequency is defined. So fundamental frequency when omega 0 equals 0 for the constant function is just 0. Okay. And once again, fundamental. So let's review a bit about the definition of fundamental period and fundamental frequency. So fundamental period is defined as the smallest positive period, and smallest period because periods are always positive. And then fundamental frequency is just defined as 2pi divided by fundamental period. And so for example, when we have this sinusoidal function a cosine omega 0 t plus phi, then fundamental period, we just look at a picture, then we see it's this length, that's 2pi divided by omega 0 absolute value, and the fundamental frequency will be 2pi divided by t0, and so you cancel all the 2pi, you get this absolute value of omega 0. Okay, and then we get some qualitative feeling between over the period and over the fundamental period and the fundamental frequency. And then we see that when we have a signal that has higher and higher, I guess it's a lower and lower frequency. So we have omega 1, omega 2, and omega 3. And the frequency is getting lower and lower. Then you see the signal is oscillating slower and slower. And on the other hand, then you see the period getting bigger and bigger. Okay. So this is an idea about the frequency and the period. So sinusoidal signal or complex exponential signal are those oscillating functions, and when the frequency is higher, it's oscillating faster, and the frequency is lower, then it's oscillating slower. Okay, and then we go to next concept now is this trivial concept is this harmonic related complex exponential. So there are a lot of complex exponential with so there are a lot of complex exponential with different frequency, and they are all periodic. And but now we want to study a property that's a set of complex exponentials that has share the same period. Okay, and so what we do is we fix some period t naught. Okay. So we fix some t naught, and we want to see what complex exponentials will have all share the same period. So what we can have is we can have a signal that has t naught as fundamental period. So we will look at this and it keeps oscillating. Then, but this is not the only thing we can do. We can also fit most oscillation between the t0. So we can have a signal that oscillates twice between 0 and the t0, and we can have a signal oscillates 3 times between 0 and the t0, etc. And so we will have those signals with higher and higher frequency, and they all share t naught as one of the period, but only for this signal t naught is a fundamental period. So say for this signal t naught will be twice the fundamental period, and for this signal t naught will be 3 times the fundamental period. Okay, so this is basically the idea of harmonic related complex exponential. They are complex exponential or sinusoidals that share the same period. So they all have t naught as one of their period, but some of them will have higher frequency and t naught will not be fundamental period. And here are the mathematical derivation of the fact. So you want t naught to be period for your signal e to the j omega t. Then you want e to the j omega t naught. Basically, you want e to the j omega t naught to be 1, and then that means omega t naught needs to be 2 pi, multiple of 2 pi, and then omega, then your omega should be k times this t naught divided by 2 pi, and 2 pi divided by t naught, and we define this 2 pi divided by t naught as omega naught. Then we see omega should be some integer multiplying this omega naught. And we derive this as a necessary condition for omega, but you can easily check that this is also sufficient for sufficient for t naught to be a period for u e to a j omega t naught. Okay. And yeah, so the ratio you can check it easily yourself, but the idea is that you just squeeze more and more period between 0 and t naught. Okay, and yeah, so our harmonic related complex exponentials are exponentials that has frequencies or or integer multiples of this frequency omega naught. Okay, so they have this form size sub k of t equal to e to a jk omega naught t. Okay, and they are basically indexed by this k. K is the number of period between 0 and t naught. And I guess the interesting special case is k can be 0. Okay, so when k equals 0, you just have a constant function here, and obviously every number is a period for constant function, so t naught is also a period for constant function. Okay, and yeah, so that's for k equals 0, and for every other k, your psi k has fundamental frequency k times absolute value k times omega naught, and the fundamental period is t naught divided by absolute value of k. And yeah, just as we show here, so this thing has fundamental period t naught, and this thing has fundamental period t naught divided by 2, and this thing has fundamental period t naught divided by 3, etc. And you can also have negative k, and then these signals will oscillate in the opposite direction. Okay, so those are harmonic related complex exponentials. And for now, they are just definitions, but later we'll see that we can use the harmonic related complex exponential as building blocks for signal with period t naught. Basically, any signal that's periodic with period t naught, then they can be written as linear combinations of those harmonic related complex exponentials. And that's why we care about complex exponential. These complex exponentials a lot. Okay. Any questions so far? If not, then let's go see an example. Okay, and so we have our signal that's the summation linear combination of two complex exponential now. Okay, so it's e to a j2t plus e to a j3t. So you have e to a j2t is a complex exponential, and it has fundamental period pi, because it's frequency 2, and 2 pi divided by 2 equal 2 pi divided by 2 equal to pi. And this e to a j3t has fundamental period 2 pi divided by 3. Okay, and then we can think about different things about this signal. So first we can think about what's the fundamental period of this thing, and then this thing has a fundamental period of pi, and this thing has a fundamental period of 2 pi. And if you want something to be a period of both this thing and this thing, then that fundamental period should be both the multiple of pi and the multiple of 2 pi divided by 3. And then that number should be 2 pi. So that's twice of this pi and 3 times of this 2 pi divided by 3. And so we know the fundamental period of this x of t should be 2 pi. Okay. This is not super rigorous derivation, but it's correct. Okay, and then we can also do some mathematical tricks. So sometimes we want to write the signal in different forms. So this signal is e to a j2t plus e to a j3t. Then we can do some mathematical manipulation and take out e to a j2.5t and live with e to a minus j2.5t and e to a plus e to a minus j0.5t and e to a plus j0.5t here. And so why do we want to write in this form? Because then now this is minus 0.5 here and the plus 0.5 here, and this can be expressed as 2 times cosine 0.5t. Okay, and so we express this as a complex exponential times cosine, and then we can get a nice expression about the magnitude of this signal. And because when you take a magnitude, then you see this complex exponential always has the magnitude 1, And so you take a magnitude, and this is just magnitude of cosine 0.5t. Okay, so this is an example of a linear combination of complex exponential. Okay, and so that's that, and let's jump ahead, and then let's go to the discrete and complex exponential. Okay, so far we've been talking about continuous time complex exponential. Now let's go to discrete and complex exponential. Okay, so continuous time complex exponential is c times e to the at, and discrete time is really similar. It's c times e to the beta n. Okay, so beta is basically alpha here, and so basically we just from those two equations you see you only change t to n. So that's really change. And so why we want to write beta here, because for discrete time, sometimes the convention is a little different. Instead of writing e to a beta, and we want to write e to a beta as some number alpha, and we'll write alpha to the n. Okay, and so sometimes people write this as c times alpha to the n. Okay, and c and alpha can be once again complex number. And once again, we see a special case when c and alpha are both real, and then you have those exponential growth function, exponential decay function, taking points at the integer values. This is when alpha greater than 0, and there is something a bit more interesting happen in this real case. That is, you can have alpha being negative here. This is something you don't see in continuous time. You can have alpha negative and real, then you have those kind of decaying and growing exponential function, but with the value dropping up, down, up, down, up, down here. Okay? So when alpha is negative and between -1 and 0, then you have those up, down exponential decay. And when alpha is less than -1, you have up, down exponential growth. Okay, so that's a special case of the complex exponential. But if you want a periodic function, then once again we back to this beta being purely imaginary. Okay, and so we kind of forgot about the alpha now, and we back to this expression x of n equal to c times e to the j omega n. Okay, and then if you write c in polar coordinate, then we back to basically this expression of x of n equal to a e to the j omega n plus 5. Okay. Yeah. I guess this is actually more important, so I should have this bigger. But anyway, for now, we care about e to the j omega n, because as we learned from last time, this 5 here and this a here. I guess this a we didn't talk about. So a is a will just be constant value of the amplitude for the amplitude, so a we don't care much about, and 5 will just be a shift on the signal, and so 5 we are also okay with, and so the real part we care about is this e to the j omega n. Okay, and then we'll discuss the periodicity of this e to the j omega n signal. Okay. And but just as in continuous time, so far we talk then, yeah, for now then we talk about the part similar to continuous time function. So this is the the complex exponential with purely imaginary exponent. And once again, you can write this back and forth between sine and cosine function. So this is basically just same as the continuous time case, except that t becomes n, so e to the j omega n can be written as cosine omega n plus j sine omega n, and this cosine omega n plus 5 can be written as a linear combination of e to the j omega n and e to the minus j omega n. Okay, and then we can see those discrete sinusoidal, we can plot this discrete sinusoidal functions. And so here are some example of cosine 2 pi divided by 12n. So it's this oscillating function. Then you can also have cosine then weirder frequency 4 times 2 pi divided by 31n, and you can also have a cosine n over 6. And so they all have a different frequency, and then you can feel this oscillating a bit faster, and this is a bit slower, and this is slower, even slower. Okay. And so far is the part where discrete and complex exponential being the same as the continuous time. But there are two major differences between discrete and the continuous time signal. And thus they all originate from the discrete signal only taking point at the integer value. Okay, because the discrete signal only have value at the integer value n. Then there are two different things on discrete signal. First is when your omega change from omega to omega plus 2 pi, you actually get the same signal. And the second different point is that the signal will be a periodic for some omega naught. Okay, and sorry, let me try to fix something. Does this work? Okay, this should. Okay. And yeah, so there are these 2 points, and let's see how the details about those two changes. Okay, and the first one is that when you change omega to omega from 2 pi, the signal is unchanged. Okay, so this is very different from continuous time signal. So continuous time signal is this e to the j omega 0t, and we just in an example we see that when omega get larger and larger, then this thing just oscillates faster and faster. Okay. And there is no bound on how fast this thing can oscillate. You have to have a higher omega naught, and this e to the j omega naught t will oscillate faster. And but this is different from continuous and discrete case. So discrete case, although the formula looks similar, you have just change t to n. But then this n take integer points. So when your frequency is too high, the signal actually doesn't see any change. Okay. And we'll later see some picture representation of this effect. But for now, let's see how mathematically this work out. So we think about we change omega to omega naught plus 2 pi, and so this e to the j omega n become e to the j omega naught plus 2 pi n. Okay, and just as usual, exponent manipulation. So this thing become e to the j 2 pi n times e to the j omega naught n. Okay. But we know that e to the j 2 pi n is always 1, because n can only take integer values, right? N only take integer values, and e to the 2 pi j equal to 1. So this is just 1 to the n, and that's still 1. Okay? So this thing is always 1, and then you see that this value is just e to the j omega n. Okay? So when you change omega naught to omega naught plus 2 pi, the signal actually doesn't change at all, because because the HR phase is always taking those integer values, and the HR phase is actually always 1. Okay, and yeah, so as we said, when omega change to omega plus 2 pi, and then we can do this several times with the plus or minus 2 pi, and so we see that when omega is changed to omega plus minus 2 pi k for any integer k, the signal is unchanged. Okay. And this basically means that, so this is a property that you should remember all throughout the course, that is for discrete signal, the frequency is basically periodic. Okay, so the frequency is periodic with the period 2 pi. That means that this omega naught is periodic with the frequency 2 pi. So when you change omega from omega to omega plus 2 pi, that changes. And that means that we only need to think about frequency from some interval of 2 pi, because everything beyond 2 pi, you just go back to the same behavior. Okay, and so we want to consider omega naught between an interval of 0 to on an interval 2 pi, and there are two popular choices. One is between 0 to 2 pi, and you can see why this is popular, because well, it's 0 to 2 pi. And another one is if you want more symmetry between your left side and the right side, you can choose between minus pi and pi. Okay, and then the idea of high frequency and low frequency is also different for discrete signal. So for continuous time signal, high frequency just means its omega has a very large absolute value, and low frequency is 0. But for continuous time signal, because the frequency is periodic between 0 to 2 pi, then high frequency, then the low frequency is actually everything that's multiple of 0. and the high frequency is actually everything that's away from this 0 and 2 pi. So it's at multiple of pi. So this is plus minus pi, plus minus 3 pi, etc. Okay, and so I guess I should plot the so low frequency signal will be very close to low frequency signal will be close to just a constant signal. And so what does the high frequency signal look like? I guess I should draw a picture here. So high frequency signal, so this is a low frequency signal is the lowest frequency signal is just a constant function, just like in a continuous case. And the high frequency signal is interesting. So high frequency signal, when you do the calculation, you see it's -1 to n. So it looks like this. You just flip up down and up down at any time interval. And you think a little more about it, you see that this is the fattest discrete signal can flip around, right? Because there are no smaller sample points. Okay, so this is a high frequency signal. You go from 1 to -1 between each step, and -1 to 1. So this is 1 -1, 1 -1, 1 -1 between each step, and so this is a high frequency. This is the highest frequency signal, discrete signal get. Okay, and this is different from the continuous time case. Any question? Okay. If not, we have 10 minutes. Okay, then let's try to finish the second point. So this is the first point. That is when you increase the frequency, when you increase omega naught, the signal doesn't get a higher frequency. Actually, this omega naught is periodic with period 2 pi. And another one is that e to the j omega naught is not always periodic. For e to the j omega 0t, we see that it's always periodic with period 2 pi divided by omega naught. But this is not true for e to the j omega naught n, because we know that once again is n needs to be integer value, and in particular the period also needs to be on integer value. So you want e to the j omega naught n plus big N equal to e to the j omega n. This is just for a periodic signal condition for some n, and so that means that e to the j omega n equal to 1, but this n needs to be integer. Okay. For continuous time case, this n can be anything, so you can always say that n is 2 pi divided by omega naught. But for discrete case, 2 pi divided by omega naught may not be integer. Then in that case, then the signal is not periodic. Okay, and yeah, let's see once again. So for this old example of a continuous time case, so you can have a higher and higher frequency, and you can always find some period. That's just 2 pi divided by omega naught. Okay. For discrete case, this is not true. Okay, so so for now, your omega n must be a multiple of 2 pi with n being the integer, and that means that omega n must be 2 pi times some integer n. Okay, and so we just move things around from this equation. Then you see that omega naught divided by 2 pi needs to be m divided by n. And m is an integer and n is an integer, so you see that the condition you have that for omega naught, for the signal to be periodic, is that omega naught divided by 2 pi should be a rational number, because it's an integer divided by an integer. Okay, so that's very different from continuous time case. Okay, and yeah, omega naught divided by 2 pi needs to be an integer, and yeah, and then you can move things a little more around a little more, and you see that the fundamental period is the smallest integer, being that so this n should be 2 pi m times 2 pi divided by omega naught, and then the fundamental period will be the smallest n that satisfies this equation. So yeah, so you start from the omega naught, then you divide 2 pi without omega naught, then you find the smallest n such that the n is a positive integer. Okay. Okay. And yeah, and so that's how you find the fundamental period, and then you have fundamental frequency. So fundamental frequency is actually not omega naught anymore. So fundamental frequency will be as our definition is 2 pi divided by big N, and that's omega naught divided by m. Okay, and so this is also different from the continuous time case, where continuous time case fundamental frequency is just omega naught, but now fundamental frequency can be omega naught divided by some integer. Okay, so this n is the difference between the continuous time and the discrete time case. And we have some example here, but we'll be short on time. I think it's more interesting to show the pictures. Okay, so we have pictures of continuous time and the discrete time signal. Okay, so continuous time signal, here we draw the cosine omega naught t, so the real part of the complex exponential. And so we see that when omega naught get bigger and bigger, then this thing just oscillates faster and faster. So we have omega equals 0 is a constant function, then omega equal to pi over 8, then 2 pi over 8, then it oscillates twice as fast, and 4 pi over 8, etc. So we have a larger and larger omega naught, then this thing just oscillates faster and faster. Okay, and then we can compare this to discrete time signal. Okay. And so omega naught equal to pi, and so this is similar. So we have a constant function and a constant function here, and omega naught equal to pi over 8. Then you see the discrete function is still a similar thing, and omega naught equal to 2 pi over 8. Then you see the similar. But when omega naught is getting around pi, then you see things start to look weird. Okay? So omega naught equal to 4 pi over 8. Then you see that when omega naught equal to 4 pi over 8, then the period is just, I think the period is 4, okay? So you only have 4 points to be one period, so the thing is minus 1 goes from 0, minus 1. Sorry, it's a bit weird. Yeah, okay. So anyway, the thing goes from 1, it just has 4 different values. So it's 1, 0, minus 1, 0, then 1, 0, minus 1, 0, etc. Okay? And then you see when omega naught equal to 8 pi over 8, then the discrete signal becomes the highest frequency. Because to match this high oscillation, then the signal taking point at the integer values become this 1 minus 1, 1 minus 1, 1 minus 1, etc. So this is the highest frequency discrete signal can have. And now when the signal go to even higher frequency, so this 12 pi over 8, then you see it's actually kind of oscillating. When you take points at the integer value, you're kind of oscillating slower. So this looks like a lot like this 4 pi over 8 case. Okay, so once again go to this 1, 0, minus 1, 0, 1, 0, minus 1, 0 case. Okay, and then you see that when we are go to 14 over 8 pi, and it kind of look like this 2 pi over 8 case, just because you can only take that many samples. Okay, and then yeah, and when we have 15 pi over 8, then you see that it's basically the same as this signal. Is this 1 pi over 8 signal. Okay, and finally when omega naught go to 16 pi over 8, because for whatever n you take, you just take cosine 2 pi n. And cosine 2 pi n is just cosine 0, and this is just constant 1. Okay, so you see that when omega 0 go from 0 to 2 pi, the signal actually goes back to itself, and you have highest frequency when omega naught is equal to pi, is 8 pi over 8. And then if we increase omega naught once more, so the continuous case will keep getting oscillating faster and faster, although the picture is too congested to see. But then you see the discrete signal go back to the same behavior as omega naught minus 2 pi. Okay, so the 16 pi over 8 signal is the same as this 1 1 pi over a signal, and this 18 pi over a signal is same as, this is 4 pi, wait, it should be, this is 2 pi over a signal, etc. And this 20 pi over a signal is same as this 4 pi over a signal, and finally, this 24 pi over a signal, which is a 3 pi signal. Once again, we have highest frequency. The signal just goes 1 minus 1, 1 minus 1, 1 minus 1, etc. And and we have 20 pi over 8. Then once again, you have this period of equal to 4, and 30 pi over 8, you have this back to period being I think is 8, and 31 pi over 8, and finally at 32 pi over 8, then this is 2 pi, then once again we have a constant function. Okay, and so that's an example of that let you see the difference between continuous time and discrete time exponential function, and because of this discrete sample points, the discrete time complex exponential actually cannot take a too high frequency. So highest frequency is when omega not equal to pi, and when you increase the frequency too much, then the signal actually looks like it's oscillating slower, and when omega goes to 2 pi, then it goes back to constant function, and it just keeps repeating itself when omega increasing between 0 to pi and 2 pi to 4 pi, etc. Okay, and I think we have a bit more exercise that you determine the fundamental period and the fundamental frequency of discrete time sinusoidal, discrete time complex exponential, but we are a bit short on time. I guess we can do some example here. Okay, so for example, we can think about when omega equal to 2 over 3 times 2 pi. I guess we only have 1 minute, so let's stop here. And next time we will come back here and let you do those exercises on how you calculate the m and n for discrete complex exponentials. Okay, so see you on next Tuesday.